In this video, we will introduce the wet layup process for producing composite parts, including techniques and their effect on part outcomes. We will perform a number of wet layups and observe the effect of different processing techniques on part quality. Some concepts that we will investigate are vacuum bag use, fiber volume fraction, void content, thermal history, and mechanical properties. After producing the parts, we will observe their attributes, including mechanical performance. Wet layup is a fabrication process where resin is manually mixed with dry fiber and placed on a single-sided mold, also known as the tool. This process is commonly performed without a vacuum bag, but vacuum bagging consumables can be placed over the layup to provide consolidation pressure and improve fiber volume fraction. Curing can occur at room temperature, but temperature may be controlled at different stages of the process to achieve different outcomes. The wet layup process requires minimal investment in tooling and equipment. Thermal properties are typically less critical for wet layup tools compared to oven or autoclave tools, which allows for a wider variety of materials to be used in their construction, leading to more economical part production. Wet layup typically produces parts with a relatively low fiber volume fraction and reduced uniformity and consistency between parts. In this demo, we will use West Systems 105 resin and AS4 carbon fibers woven in a 204 gram per square meter 2x2 twill pattern for all layups. Our tool will be a flat sheet of glass. We will apply liquid mold release to prevent the resin from adhering to the tool. Some samples will be vacuum bagged with disposable consumables and some will not. For the vacuum bagged samples, we will place peel ply next to the laminate, a permeable self-releasing fabric that allows resin and air to pass through it while preventing the resin from adhering to the rest of the consumables. On top of the peel ply, we will place breather cloth, a loose and permeable polyester fabric that absorbs excess resin after it passes through the peel ply and allows air to evacuate out of the layup to ensure even vacuum pressure. For thick laminates that may bleed a lot of excess resin, multiple layers of breather cloth may be beneficial. We will locate the vacuum port near the center of the layup under some additional layers of breather cloth to ensure good airflow. Around the perimeter of our layup, we will place sealant tape to form an airtight seal to the tool. We will place the vacuum bag over top of our layup and seal it to the sealant tape. We will then pull vacuum on the layup as it cures. Cutting composite fabrics can produce irritating fiber fragments. Resin should not contact your skin, eyes, or clothes. When performing a wet layup, gloves, a lab coat, dust mask, and safety glasses at minimum are commonly worn. Additional safety equipment may be required. Consult the material safety data sheet of the materials that you are using for recommendations. The first step in performing a hand layup is preparing the fabric. We will use a pattern, rotary cutting tool, and rubber mat to cut the fabric. It is important to cut the fabric accurately to ensure consistent fiber alignment and to reduce post-processing time of the final part. Fabric waste is also minimized if an efficient tool is used and the plies are cut neatly. For these samples, we will weigh our fabric plies for each part and record the values. These will later be used to calculate our fiber weight fraction. Our vacuum consumables are also cut to size and placed aside. After our fabric and consumables are prepared, we will begin preparing the resin. We will be using 2-part epoxy resin, which will begin to cure after the resin and hardener are mixed. We will calculate an appropriate mass of resin based on our fiber mass and estimated final fiber volume fraction, plus a small amount to ensure we have enough. The cross-linking between resin and hardener molecules that occurs during curing is exothermic. As the temperature increases, this reaction occurs at a higher rate. As a result, large volumes of resin mixed in one container can heat up to dangerous temperatures quite quickly. Here, we have mixed 150 grams of resin with a gel time of 20 minutes in a cup. It can be seen that the resin starts to heat up and begins to produce vapors and melt the cup. It is advisable to mix fast-curing resins only in small quantities at a time. The ratio of 2 components is specified by the manufacturer, and deviations from the recommended ratio can have an effect on properties. A scale is commonly used for accurate measurements of the 2 components. If mixing by hand, a container with flat sides and bottom and a mixing tool that can scrape the sides and the bottom of the container can ensure the components are fully mixed. During the layup process, 1 ply of fabric is laid on the tool and the resin is evenly applied to the fabric with a plastic paddle. It is important that the tool used to spread the resin does not have any sharp corners that may damage the fabric weave. Ensure that the fabric is fully saturated with resin. If areas are missed, there may be a dry spot in the final part. Avoid placing excessive resin into the laminate as it can lower the fiber volume fraction and waste additional resin, although excess resin will mostly be removed from the part by vacuum consumables if they are used. While placing the plies and spreading resin, avoid deforming the fabric. Wavy fibers can reduce mechanical properties and affect the appearance of the part. For 3 of our samples, we will slightly deform our fabric while laying them up to observe the effect it has on part outcomes. After all plies have been deposited, we will place the vacuum consumables on some of the parts. We will place the peel ply against the laminate, followed by the breather cloth. A portion of the resin will be pulled into the consumables and increase the fiber volume fraction of the part. Breather cloth also helps to remove entrapped air, reducing large voids in the laminate. The samples will be left to cure at room temperature. After our samples have cured for the recommended time, we can remove them from the tool. The time to demold can usually be decreased by heating to a moderate temperature, however this can slightly increase deformation due to thermal expansion effects and physical aging. The degree of cure of room temperature cured parts may be slightly increased by performing a heated post-cure in an oven. The effects of heated post-cures of varying temperatures and lengths are resin dependent. Some resins, such as the one we have selected, will continue to cure at a slow rate for weeks or months at room temperature, but can be accelerated to a high degree of cure with a heated post-cure. The manufacturer's recommended cure cycle, also known as the MRCC, is a good starting point to obtain a suitable cure. One set of samples will be oven post-cured at 38 Celsius for 24 hours. These values were suggested by the resin manufacturer. A second set of samples will be post-cured at 80 degrees Celsius for 8 hours. These values are intended to show the effect of exceeding the recommended cure temperature on mechanical properties. The remaining samples were left at room temperature for 48 hours prior to testing. Now that we have produced and post-cured all of our samples, there are a few ways that we can assess their quality. Observing the surface finish on the mold side, both the vacuum-bagged and non-vacuum-bagged samples have surfaces which may be considered defective depending on the application. The non-vacuum-bagged samples entrapped a considerable amount of air which produced small areas where the resin does not follow the mold surface. Over the entire surface of the vacuum-bagged sample, the surface areas between the toes are not filled with resin, producing a slightly patterned surface. On the reverse side, the peel ply has left a matte surface, while the open-air cured sample has a glossy but textured surface that shows the toes of the fabric. If we look at the samples under the microscope, we can see that the peel ply has transferred its tightly woven fabric surface onto the part. The surface of the non-vacuumed part has clearly visible toes saturated with resin. The sample that was cured at 80 degrees Celsius has darkened slightly, but the suggested cure had no effect on part appearance. We will now weigh the parts to calculate the fiber mass fraction. A part with a higher ratio of fibers to matrix will generally have superior mechanical properties as long as the fibers are fully saturated with resin. We can see that the vacuum-bagged parts had a consistently higher fiber mass and volume fraction than the open-air cured parts, which typically means higher strength and stiffness per mass. After sectioning the samples, we can observe the internal void content. The vacuum-bagged samples had consistently fewer large internal voids, but did have considerable amounts of smaller porosity. The voids tend to be oblong instead of spherical, as the fiber bed has been compacted by the consolidation pressure of the vacuum bag. It is also apparent that the thickness of the vacuum-bagged part is smaller than the open-air cured samples. We will now perform a mechanical test on all of our samples. The purpose is to compare the effect of manufacturing parameters on component-level mechanical performance and will not follow any specific test standard. We will place our samples in a 3-point bend test and record the force displacement curve. The results are shown here. Note that the maximum stress is calculated based on the mean thickness of the laminate, so if a thicker laminate reacts the same force as a thinner one, the thinner one will develop higher stresses before failure. In agreement with theory, the vacuum-bagged samples which had higher fiber volume fractions also had higher strengths. The volume fractions are plotted in red according to the right-hand axis. It is notable that the stiffness of the samples varies more than the strength. Another result we can observe is that the difference between the expected strengths calculated by the fiber volume fractions and respective strengths of the fiber and resin is considerably higher than the achieved strengths of the samples. The differential is consistently larger for the vacuum-bagged samples, which achieved a higher fiber volume fraction and have a higher theoretical strength as a result. It is notable that this trend is reversed in the case of stiffness, with the open-air cured samples having a larger differential between theoretical and measured stiffnesses than vacuum-bagged ones. We will discuss a potential mechanism of this shortly. The samples which were post-cured according to manufacturer's recommended cure cycle were stiffer than the samples which were not post-cured, but were similar to the samples which were held at a higher temperature for longer. The post-cured samples had strengths in between the two non-post-cured vacuum-bagged samples, both in absolute terms and relative to expected strength based on fiber fraction. The high-temperature cured samples had the highest strength and high stiffness, indicating that they may not have been held at high enough temperature or for long enough to begin to degrade the matrix. The samples with misaligned fibers did not have definitively lower stiffness than the other vacuum-bagged samples, but did have the lowest strength. For all samples, fiber volume fraction was calculated. The fiber weight fraction was calculated based on the weight of the fibers and the weight of the final part, and then this was converted to a fiber volume fraction estimate with the densities of the fiber and resin. Porosity and void content must be determined, which could be done with microscopy and image processing software, but was not due to the large number of samples and the preparation required to produce an accurate result. Instead, the thickness was measured and the volume fraction is calculated based on the area, weight, and density of the fabric as well as the fiber weight fraction. Since woven fabric was used, the samples had a slightly rippled surface which has different thicknesses in different areas. Thickness measurements were taken in multiple areas and a portion of the sample thicknesses were checked for agreement with thickness measurements taken with a microscope. The porosity and void content of the samples was calculated by comparing the expected sample thicknesses based on the fiber and total mass and the component densities to the measured sample thicknesses. The parameter that had the greatest correlation with calculated porosity and void content was the use of a vacuum bag. Contrary to what is typically expected, the samples which were not vacuum bagged were calculated to have lower porosity and void content than the samples that were vacuum bagged. This result appears to be in agreement with microscope images of the sample cross-sections, which show extensive porosity in the vacuum-bagged samples and a smaller number of voids in the wet layup samples. A potential explanation for this is that entrapped air in the vacuum-bagged samples will expand to a larger volume in between the fibers and displace some resin into the vacuum consumables, whereas entrapped air in the non-vacuumed part will remain at the smaller volume that it occupies at atmospheric pressure. There is a correlation between increased porosity and reduced strength relative to the expected strength based on fiber volume fraction, as seen in this graph. Porosity can reduce strength by reducing the effectiveness of the matrix at transferring load between fibers and between plies, which can reduce the strength of the laminate even if they have higher fiber volume fractions. Overall, we can observe that higher fiber volume fractions produced by vacuum bagging are associated with superior properties compared to lower volume fractions produced by curing without a vacuum bag. All tested samples had lower properties than predicted based on their volume fraction. It is also notable that there was a difference in properties between the samples which were laid up in series or parallel, which shows that subtly different manufacturing processes can have an effect on part outcomes even if most process parameters seem similar. Our value of these tests is that they demonstrate the variability inherent to the wet layup process. These results are from a 3-point bend test of a relatively thin part made with woven fabric in a wet layup process. If any parameters are changed, such as switching from woven fabric to unidirectional or performing a different test or with different sample geometry, the results may also change. We will now perform a wet layup of a more complex part to showcase the effect some process parameters have on part quality when difficult geometry is present. For the first part, a vacuum bag will not be used. Resin with a 20 to 25 minute pot life is used, and the first layer has begun to gel while the second layer is being saturated. This can help hold the first layer in place while it is being positioned and wet out. It is important that enough working time is available to ensure that the part is evenly saturated and that there are no wet or dry spots. After removing the part, we can see that it is generally well saturated but has a few small dry spots. The inside surface has some porosity throughout. The outside surface is quite consistent but is not smooth. The toes of the fabric are remarkable and have created a patterned surface. A fiber volume fraction of 38% was calculated, typical for a wet layup cured without a vacuum bag. For the second part, we will use a vacuum bag. The fiber deposition and resin saturation is similar to the previous part, but it is slightly less critical that resin is distributed evenly as excess resin is removed via the vacuum consumables. For this test part, we will use peel ply and 3 layers of breather cloth to ensure that all excess resin can be removed. If insufficient layers are used, the resin can soak all the way through the breather cloth, and the lack of additional permeable material can reduce the volume of resin removed from the part and reduce fiber volume fraction. As vacuum is pulled, we can double check that all inside corners are not bridging and the fabric and consumables are held tightly against the mold. We included loops of extra vacuum bagging material, called pleats, around the edges to ensure that there is enough vacuum bag to reach into all contours of the tool. After demolding the part, we can see that we had some fiber bridging in the corners. The fabric was not deposited all the way down into the corners or had been accidentally shifted after it had been placed. A fiber volume fraction of 55% was achieved. It is important to ensure that the working time of the resin is sufficient to deposit all fabric plies and accurately position the vacuum bagging consumables. The same resin was used as the previous wet layup part, with a working life of 20 to 25 minutes. Switching to a longer working life resin gives more time to precisely position and saturate the fabric before pulling vacuum. The working life of the resin can also have an effect on fiber volume fraction. If the vacuum consumables are placed and vacuum is pulled after the working life of the resin has been surpassed, it will have an increased viscosity and will not flow into the consumables as readily. Excess resin will stay in the part and reduce fiber volume fraction. This part achieved a fiber content lower than some of our previous test samples, which were vacuum bagged before the working life of the resin had been exceeded. For our third part, we will use a resin with a working time of 4 hours. We will also cut our fabric slightly differently around the areas with tight inside corners, cutting a slit in the fabric, also known as a dart, and adding additional piece of fabric to cover exposed areas. The smaller fabric piece is easier to position into tight geometry without bridging. Alternatively, or in conjunction with smaller pieces of fabric, individual toes of fibers could be placed inside corners to ensure that they contain fiber and not just resin and air. After removing the part from the tool, we can see that there is significantly less bridging than the other two parts. There is generally less fiber misalignment as well. The measured fiber volume fraction is 55%, equal to the second part. One factor to consider when selecting resins with a long working life is that the time to reach a high degree of cure is also extended. The third part was removed from the tool after 24 hours at room temperature. It was then trimmed to size and the dust was removed with a moist towel. The dust became embedded in the outside surface, which did not occur with the second part, which was made with resin with a shorter cure time. This was likely caused by the very slight softness and tackiness still present in this low curing resin. To prevent this, a heated post-cure or increased time at room temperature could be used to increase the degree of cure before the part is processed. In a production environment, either of these requirements could increase the cost of the part, as more storage space or equipment would likely be required to produce parts at a fixed rate. A factor that has a significant effect on part outcomes is laminator skill. These parts were fabricated by a laminator with some previous wet layup experience, but part quality can be improved by employing professional staff and producing a number of practice parts. Fiber alignment, bridging, wrinkling, and uneven resin content, as well as fabric placement and uniformity of appearance, are all improved with laminator skill. After performing a handful of wet layups and observing their outcomes, a few conclusions can be drawn. If a requirement for a part is low weight, high mechanical properties, and repeatability, the superior fiber volume fraction produced by vacuum bagging will typically outperform an open-air cured part. When a part has many tight curves or corners, a vacuum bag helps hold the fabric in place against the tool. Vacuum bagging may also reduce large voids within the laminate. A disadvantage of vacuum bagging a part is increased layup time as well as equipment and consumable cost. Preparing the vacuum consumables and placing the bag for the large parts took about 30 minutes and required a vacuum pump. In a production environment, a reusable vacuum bag fabricated out of more durable rubber can reduce layup time and consumable cost. A limitation of vacuum bagging is that it benefits from a more stiff tool than open-air curing and requires a non-porous tool. Vacuum bagging produces forces on the tool which can deform it and hurt part tolerances if the tool is made out of very soft material. Vacuum bags are susceptible to leaks which can draw air into the part and create porosity if not sealed before the part cures. Different surface finishes and qualities are produced by the two processes. If a glossy and somewhat smooth surface is desired on the opposite side of the part, this can be achieved by saturating the fabric with additional resin and curing without a vacuum bag. Different vacuum bagging consumables produce different surface finishes, so with some experimentation, the desired surface may be obtained with vacuum bagging without post-finishing operations. Results of performing heated post-cures was somewhat inconclusive. One other effect that post-curing typically has that was not explored was an improvement in mechanical properties at elevated temperatures. If the maximum matrix strength, stiffness, and hardness are desired, or the part will be in service at elevated temperatures, then a heated post-cure may be beneficial. The skill of the operator is also a large factor in laminate quality, as poorly placed fabric and dry or overly saturated fibers have the potential to reduce properties and aesthetics. Another important conclusion illustrated by these layups and tests is that a high degree of variability is inherent to the wet layup process.
Thanks for watching. To see more virtual labs and learn more about composite materials, make sure to subscribe to the CKN YouTube channel.